In Lab 10, we explore the property of gas. As we studied in the class, when temperature is high enough, the collection of molecules take the gas phase, right? When high temperature, where they are farther apart in their liquid than they are in the liquid or solid phase, and actually they travel faster. In this lab, we're familiar with the concept of the equation of gas property in macroscopic. We can explore overall their properties in terms of the overall volume of a collection of gas molecule and pressure as a whole, and then the temperature. And these three, for the ideal gas, satisfy this equation over here. This equation, okay, P times V, pressure multiplied with the volume, equals temperature, proportional to the temperature. And of course, this N is the number of moles in your system. Moles, when those of you who take chemistry and you know number of moles related to number of particles in the system. And R is the ideal gas constant. So you just remember P, pressure times volume. If the temperature is fixed, is a constant, which means when you have pressure goes up, volume will go down. But then these three quantities, pressure, volume, and temperature. So we explore the relation between these three. They satisfy this equation. And now, of course, that's assume it is ideal. So if items can be modeled as structureless particles, and actually many gases qualify these properties, and so we can call it ideal gas. Otherwise, if we have considered the structure or internal motion, it is a non-ideal gas. In this class, we probably don't explore the non-ideal gas, but even though that's not that important, but then we will explore the ideal gas. Okay, and many gases like inert gas, helium gas, and hydrogen gas, and many gases when at relatively high temperature, they're very close to ideal gas. So when they are farther apart, they can be considered to be just small particles with structure without any internal structure. So ideal gas equation. So now we're going to use to start with, we're going to use this site, but okay, to start. However, this site is actually updated. Okay, in particular, I have included the software in this folder. So, but even though I'm going to show a demo over here, but of course, this new software has some feature, but missing some feature that we will need. So, in fact, we're going to use this, and this software is included inside here. So if you go into the folder and then gas properties, which is a Java program, you can start this one, and you will see this, okay, to actually do your experiment. So it's offline. This one is online, but it's a software included in it runs on PC, or it may even run on the Mac. I don't know, but it definitely run on PC, on school computer, as I'm running it now. Okay, so let's close this for a moment, and just let me explain what the idea is here. Okay, so we will explore more about this equation in the class, but let's just do a little bit analyze to see what we are trying to explore. So ideal gas law, as we said, pressure of the gas and times the volume of the gas, and it will be equal to something proportional temperature. And then this N and R are two constant. When a constant is like number of moles, okay, number of moles, which means each mole has like 6.02 times 10 to the 23 number of so that's lowercase n. Okay, number of moles in here in this equation, and then you have R is the ideal gas constant 8.31, and you can always find out what's the value, and we will have a lot of homework involving this equation, but since this is the lab, we just qualitatively what we're dealing with. Okay, think about it mathematically. All right, so you have three variables, okay, but with your simple mathematics knowledge, if your equation has three variables, if one is fixed, okay, and you can have vary one, which have a plot of vary one and changing the other one, okay. Of course, if two of them are fine, you can find the third one. But here, if one of them is fixed, then you have a graph. Okay, for example, if you have the gas, if the volume is fixed, imagine you have a balloon. Okay, you have a balloon or have some pressure cooker. The volume is fixed, but then there's gas, steam in it. Okay, and then you have a plot of temperature versus volume, pressure versus temperature. Then you expect an increased plot like this. So this one, increased plot. So if you have volume fixed, okay, and then on the other hand, if you have temperature fixed, all right, and temperature fixed like you have a balloon, basically at a fixed temperature, okay, but then you have a plot of P versus V, and if you divide this P to the other side, and then you will have volume versus pressure plot. It will look like this, so which means going down like a curve as an inverse relation or reciprocal relation. So in other words, if you have pressure is high, when you squeeze the balloon and the volume goes down. If you let pressure low, you let go and the volume will expand. You will have this pressure. Okay, and of course same equation, and if you have a pressure fixed, all right, you have a fixed pressure, and it's like you have a syringe, okay, and then put in there, and if you have temperature increased, and the volume will go up, okay, with pressure fixed. So these three, now we are going to in this lab explore these three, okay? Remember this, PV equals nRT, but so you run P times V, pressure times volume, equal to mole number, gas constant, and times temperature. So that's called ideal gas law. And so involving three variables and two constant. So let's go to this site to further see what that equation actually means. So here we have, now you can do the demo yourself. So you have some gas. All right. So in this you can play this. I suggest you play with this to get an idea. And then if you say, well, like let's do this plot, okay, and P times V. So let's do an experiment with this equation. Say with volume fixed, which means constant. Then this P and V simply have a linear relation. So whenever you have higher temperature, you have higher pressure. Even higher temperature, even higher pressure. It's a simple relation. So now let's visualize this one. So then we have volume fixed. So hold constant. You click this number. Hold constant. All right. Hold the volume constant. Then there will be pressure over here, or atmospheric pressure, and temperature. So now you see it's at this moment it's 24 atmosphere pressure. Now 300 degree. Now let's increase to 400 degree. So what do you think of the temperature? Pressure. See, the pressure goes up. So 420, because this goes faster, Okay, this goes faster. It's hitting on the wall, stronger, same number of particles, and obviously you see it was 20, so now it's 35. Now let's make it to 600 degree. So something like 600 degree, and then this move faster, and the measure pressure is measured. The pressure is even higher. So if you hold the volume to be constant, and then you will have a simple relation between pressure and temperature's linear relation. The higher the temperature, the higher the pressure. So that's explore this relation. So this one. Now let's see how about this one. You fix a constant temperature like you have a balloon. You squeeze the balloon, and then the volume is going to go down. Or you increase pressure. Let me go the other way around. So you can plot. Of course, you can. Whenever it's a reciprocal relation, then you will have a. Let me put. This one be more easier. So also like this. So basically, you will say P equals nRT. Those are because the temperature holds constant. V. It's a reciprocal relation. When V goes up, and so then it goes down. Or you can solve this the other way. V equals nRT divided by P. So then you will have also there is V and P. So basically it says you make a volume large, you have less pressure. You squeeze volume small, you have a higher pressure. So then let's look at that. So let's see, heat the temperature constant. So now it will allow you to add ice or add fire. So temperature, they move at the same speed. Now let's vary the volume. Okay, look at the pressure. So if I make the volume smaller, what do you think about the pressure? Yes, it's going to increase. Okay, so now you make it volume smaller, right? So now see it's 51. Now you make it smaller. See, it's higher. See, it's the same temperature. Okay, same temperature, which means the same average speed. Why is that? I think you can see that because they are bending on the wall because the volume is smaller. So then the area is smaller, right? Because the area is smaller. The area is smaller, but the same number of particles is more dense. And more dense, the bending is stronger, right? Because it's squeezed together. So that's explanation that just show that why. So that's called a microscopic explanation of macroscopic properties. So if you make the pressure, make this even smaller, so then there will be much less area, at least on the bottom. And this move the same speed, more dense, the pressure will be even higher. So that actually fit very well to your basic sense. When the squeeze, of course, the pressure is higher. But for the gas, you can see that they are more same speed, but they are more close together. But then on the wall, on average, there are more collisions. There are more collisions because they close. So of course, then you will have, when they're small, okay, when the V goes small, V go loud. V go large, pressure go low. So if you go large, and pressure go low. So there's less heating. So it large, and pressure go low, right? So very large, okay, and pressure go very low because you have bigger area and less heating. So then that reflect this relation. So, okay, volume, when the volume is large, pressure goes drop. The volume is large, pressure drop. Volume is large, pressure drop. When volume is huge, the pressure goes to zero. But on the other hand, if your volume goes small, and pressure goes high, you squeeze. So that's this relation. So then that's this relation. All right. So now, so that's when you heat. You can have three different kind of plot. Now, we had this one already, P times V. So temperature is high, hold pressure is high. Temperature high, pressure is high. Now, and also volume pressure, I call it expansion. Okay, and to do that, so think about something like a balloon, or or some kind of a plastic bag with air. Okay, and when you have a higher temperature, it will expand bigger. And higher temperature, expand bigger. Okay, but of course that's with the same pressure. Okay, same pressure. You hold the pressure of the constant simply because V equals and that then N R T divided by P. But this one you press is constant. So all three of these are constant. So that simply changing with this. So you go temperature goes up and that goes up as well. So then you will have this plot. So this ideal equation. So from here, that's all from this equation. So now let's see. Let's do that. We hold the pressure constant. Okay, V is going to vary. Okay, yeah. So now V is going to vary. So we cannot adjust V, so we hold on. So now we lower the temperature. You see, colder. Pressure is constant, right? Pressure. Think about the outside is the same pressure. All right, same pressure. But then if you lower it, lower temperature, it require squeeze smaller so that it can, because outside the same pressure, if you constant pressure, but then if you change it to cooler, then the volume is smaller. Okay, cooler, volume is smaller. All right, all right. I think you're used to the other way around. So when the same pressure, but if you're hotter, and you need more volume. Okay, you're hotter, you get more volume. Hotter, more volume. Same pressure, which means, so pressure cannot be held constant anymore. Volume is large. But that's just limitation of this software. So you see, if you hold the pressure constant, hold the pressure constant, and of course cooling down, once again, cooling down, smaller volume. Cooling down, smaller volume. So that repressed. So all these three relations covered by the same formula. This is called ideal gas law. Of course, you can also vary this. If you have less number of particles, you think about it. If your fixed temperature is the same, and if you have more particles, this product will increase. So more particles, this will have more particles in. The volume will be bigger. So if you just pump in more, you see, okay, it will have more particles. We will not explore that, but that's an interesting experiment to do. So that's where we're going to explore this equation. Okay, and this is in the back of this file. All right, let me stop this one. But in fact, so that's a demo. Okay, with that explanation, we're going to do what we actually do in this lab. The first experiment, I want you to explore the thermal energy and temperature and pressure dependent, which is basically a straight line. What you actually use is actually this software, and they are updated. It used to be online, but actually I downloaded this. You just double click this and it will start. And so now what I'm going to do, introduce 200 first. You see, you do the plot of this in the data chart. What you would do is this. So you will do temperature and with a fixed volume. You want a fixed volume at 6 nanometer. You have a ruler to introduce that 6 nanometer, and then you can change the temperature. Obviously the pressure will go up. Change the temperature, pressure will go up. At the same time, you see the velocity goes up because temperature is velocity. And you also calculate the kinetic energy of the average speed. For example, I calculate something. Don't just copy this number. I just give you an idea what the number would look like. Introduce 200 of them. So that's the procedure here. And so you can just introduce 200 heavy species. You can simply go up, okay, or probably you can simply type 200. So there will be, okay, there will be 200. Okay, and then of course you will put here measurement tools, and then you will say you need a ruler, which means you can measure the nanometer. What you set at 6 nanometers, so you can adjust this to be the size to be 6 to start with, and then so you fix volume. So that's volume is fixed. You don't do anything, and then you will, and then what you increase temperature use 2. So that's how many degrees, and actually so then you start from 1 degree, you go down low. So temperature is low, you see this slower, and then you do you collect all this data with the temperature be the independent variables. Okay, I suggest you first experiment go from 0, 1 to all this. Don't have to go increase just by 1, but just get this many data. And then average speed, where do you get a speed? There's a reading, you click this one. Energy histogram, probably you don't need energy histogram. And species information, you click this, and the velocity will be showing up there on the pop-up, hopefully, yeah, so over here, the velocity, speed, and then you enter the velocities here, right? So for example, this one, velocity, I will be going in here. So now it's how many degrees? And then you will calculate the average kinetic energy, because you have a total energy, total thermal energy, how much energy you have, and then that's just 200 times each one of them squared, and then you enter here. In fact, you don't have to exactly do the calculation with the calculator all the time, but then later when you do the plot, and then you use Excel, you put in the formula, and you enter this, and then you will have and then at this temperature you will have this pressure. So let me just do one, for example, at 70 degree, okay, and then you will have the average velocity and pressure. Okay, so 70 degree, I will do, so I'll go up to lower to make ice, do 70 degree. So you don't have the exact, also all the microscopic system are fluctuating. 70 degree. Now, what's the speed? So over there, 203. So the pressure is 0.25. So then just pretend I am a student. So 201. Okay, and what is pressure? Go over to here. So pressure is over here. 0.25 atmosphere pressure, as we discussed in the class. Okay, 0.21. Mine may not be exact. And then you fill up this table. You do all this, and you can do this calculation. But since you have, say, 201 squared divided by mass, just take us 1 atomic units, as we talked about it. I will ask you a question: how much is 1 atomic units? But here, I don't be very specific. Just take that as 1, okay, and 1 atomic units. Then multiply, you get this number. So 200 squared and divide by 2 and multiply by 200, you get, see, 200 is a very large number. You get this, and now you don't have to do exactly right now. But when you take data and when you do plot, and then that's you fill up this data, and you will see that basically just give you some impression of how temperature goes up and pressure goes up, and then that is due to these collisions on the wall. So pressure is just average hitting or impulse on these walls surrounding this gas. So then when you fill up this, and then you will do a, like usually I always want you to do a plot, do the pressure versus temperature and pressure versus your two plot, thermal energy. Okay, thermal energy is the total, which is the concept we will talk about which is a collection with all, adding all this up. So since we have 200, we add up 200. If we have a trillion, we add up to a trillion. But then you have pressure versus temperature. So once again, I will show you a sample plot in this. Where's my? So this folder will be uploaded online. So then, for example, I just give a few of this. So then you have pressure versus temperature. Yeah, supposed to be a straight line like I plotted because that's ideal gas equation. And then for pressure versus thermal energy, then you will plot this versus that. Okay, if you want to select and pick all the two columns, on left one you select and then you hold the control key and then you shift and control and then you can choose these two. Okay, and then choose this one and choose this one and hit control and choose this and plot these two. I have a video last time to show you how do you plot pick, then of course plot this one. Somehow at this moment, because the video is running, I don't want to go too much on this one. That's simply Excel script. Then you also similarly get one of this. Okay, I get a plot, and then you get increase settings. Then you want to insert the plot here, and so that's this one, and also repeat the process. Okay. See, we go from only go to 270 degrees, and you continue, or it's not repeat, but from 270 go all the way to do the same thing, and continue do this table, and until you see when you have very high pressure, you see, let me go back to, so you stop at 273, now you're going to continue this, and keep going, increase temperature. Okay, and do the same thing filled on the second table, which is basically an upper range of temperature. So you see the temperature, when you increase the temperature, and then the pressure goes higher. Okay, simply because of the banning. But at some point, just record, go to something about almost 1000 degrees. Let me screw over this, and then, or until the lid over here will be, see, that goes up. This is too high because that's, once the lift off, it go out. Then the pressure, temperature will be down, pressure will be down too, because there's no more hitting on the wall. So the point here, the moral here is to see how, what the origin or mechanism of the pressure and an ideal gas equation. Pressure versus volume, volume versus temperature, temperature versus pressure, how they change. All three of these relations, or actually 6 relations, are covered in this equation. So, and then we do 2 experiments. Second is like pressure, volume pressure relation under constant temperature, as we have sketched. Continue previous setting, 270. Fix it at this degree by clicking temperature constant button. So now the second experiment asks you to this volume and pressure relation with constant temperature. Okay, and so first you say constant temperature, which means you're not going to change the temperature. Click this constant temperature, and then you can, in other words, vary volume, see how pressure changes. Vary volume, how pressure changes. Okay, and that will, of course, you close the lid, and then give you some species. You do the same thing, and constant temperature. Let's keep, of course, before you hold the temperature, you will put your heat up to make the temperature goes up to 173, something like that. Make it higher. You see, it will take a while for it to heat up because the thermal conduction takes time. So temperature goes up. That's sort of like a preparation stage. Oh, 270 supposedly, roughly. Okay, so then once you're there, although I just go down 273, as I said, So 273. Okay, if you really cannot get exact to 273, it rounded off by 1 or 2 degrees. It doesn't really matter that much. So let me do 274. Okay, that's good enough. So constant temperature. Now we're going to vary the volume. The unit we just use because we only change one side. Okay, it will start with how much? Actually we start from high volume, 70 degree, and slowly varying temperature from 6 nanometer to 2.2. Okay, because I already did. Okay, so then volume. So for example, like you have here 6 nanometer. I enter here. What is the pressure? Okay, and so what is pressure? So it's 1.1. Okay, just say 1. So that's 1 atmosphere pressure. And velocity, you can also count the velocity, and of course at the end you will see velocity is 406. Okay, up there. Velocity 406. So now basically you going backwards, okay, and squeeze it, make it smaller, 1 nanometer, but this is actually very quick. So you go to 5. Oh, you squeeze it. Obviously when you squeeze it, then the closer the same temperature, and then it hits more because it's more packed. You can always also think the pressure is force divided by volume, okay, by area, but area is smaller, and then of course pressure would be higher because the same amount of hitting. So it's 1.3. So so it's 5, and pressure is 1.3. is higher because smaller. And velocity, if you see, velocity is 406, no, 407. So yeah, so okay, 407. So it's bigger. Okay, not that much bigger. So then you will see a number of particles, average speed. All right. So then let me do one more time, and so then you make it 2, squeeze smaller, okay? And because see, whenever it's constant temperature, the temperature is constant, the speed is constant. It's not changing much, okay? So temperature only depends here. You say temperature, we hold the constant, so you see the speed not changing much. Okay, but it's supposed to be the same because temperature is nothing but velocity, kinetic energy. Well, temperature constant means kinetic energy constant. So that's still 402. Okay, but and also all the summers, yeah, so you make it 4. So then, but still 402. But it should not changing much, but it's just a fluctuation. Okay, so theoretically, still almost same because the temperature is constant. And then you will have what is pressure? But pressure obviously is very significantly with volume. And volume goes small, pressure go big, and that's really fit what you normally think. If you squeeze, and pressure will be high. Squeeze means smaller volume, and you get bigger pressure. Even smaller volume, even bigger pressure. So now if you say, I'm not going to write it down now. So even smaller, so the pressure is even bigger, right? So it's 3 now. You can do even smaller, so even smaller because that smaller pressure is even higher. So that's it. So then you're expecting a decreasing function like that. So then you do that, and then you will do, once again, you will have a plot. And then I insist I have a more requirement. Once you have a plot, you will get an Excel plot. I'm not going to show you Excel plot now. And there is another sample data. Okay, and so this one. So it goes up. The pressure goes up, pressure, volume goes up, pressure goes down, depending on which one you prop versus which one you put on the horizontal axis. So it's all one go up, the other one go down. So this could be pressure go high, volume go down, or you squeeze and go down, or the other way around, pressure go high, volume go up. But then you plot here volume and pressure and so velocity stay the constant. You can plot. No, if you want to plot in fact I want you to plot is pressure versus volume. Okay, volume on the horizontal axis, pressure on the vertical axis. So that's what you're going to plot. And you sketch the plot, enter here. And also one more step, I want you to do a trend line fit. So for example, pressure versus volume, you put this, you select this two, and then insert a plot. So that's this. Okay, you put a title, volume, and then you will put here, you select it over here, you can insert a fit. In other words, you will get an equation. You go down here, a trend line. Okay, a trend line. Then over here, so there's a trend line. Actually, more options, so you can get a trend line, and more options, and then you have more options. Then you will have, see, all these are the options of the line, the equations. I will show you. In fact, in this case, it's not linear, it's power. Okay, and actually it's, so I click the power. In fact, the power is a negative power, display equations. Okay, and it's negative power, so that's the equation. Negative 0.8 is 1 over. So we're not getting to this that much, but it's 1 over is to the negative 1, which means V is reciprocal of P, so, or vice versa. So then you will do a plot, and but you should put also titles. For example, here we have pressure and volume. So you put the title here, and so here you will have volume. Okay, I just say nanometer because I just, and then pressure over here. So then you cut paste and insert there and just do this. So I will on purpose delete this one. Okay, so that's what you do with this lab, and you do this pressure, and then hopefully in this process, so once again summarize what we're trying to do is try to explore the relation between pressure, volume, and temperature of ideal gas. Okay, so much for this. Hope you enjoy it. If you have a question, we can always have a separate discussion offline, either through Zoom or in class. Bye bye for now.